Well, hello, everybody. We're super excited to have you here today at SAS Innovate. We're going to be talking a little about the new features in SAS Econometrics, and we've got Jilong Chen here today to give you guys an amazing presentation. We're super excited to have you, and we hope you're just excited to see us. So, without further ado, Jilong Chen.
Yeah, thank you very much. And hello everyone, I'm Xilong, and I'm a senior manager at SAS. And today it's my honor to talk about some new features and performance improvement in SAS Econometrics. SAS Econometrics includes the SAS ETS and consists of 71 procedures and data engines and 21 action sets. It's based on the VIA platform, so it supports much more programming languages than just SAS. And it also that could do the parallel computing and in-memory data access, so that to face the challenge of the big data, big model, and big simulation. It consists of all the popular econometrics modeling tools and time series analysis tools for the different kind of business requirement. And today I'll talk about one new feature and two performance improvement happened in last year. The first new feature is related to the CSSM procedure, which is a cloud counterpart of the PROC SSM for the state space models. State space models might be the most popular time series models in this field, and it has been used in engineering, science, and economics, finance, almost everywhere. Because in general, almost all time series models have the state space form. And today we're talking about a new feature, and before that I just introduced the concept of smoothing. Here we use a general smoothing concept. It's just like that you observe everything, and then how do you know that the distribution of a hidden state at a certain time point? If this time point is in the past, this is the old way we're talking about smoothing. But if it happens just at present, then it's the filtering. If it happens in the future, it's forecasting. But all these things is just based on all the information, how you interpret it at whatever happens at one time point. But what happens if you require, and in fact in most real world case, you require to have a range, have the joint distribution of a range time point. And in fact, before this new feature, there almost no way to get that. But now that we introduced the simulation smoother, it could draw the samples as many as you like, and from the true unknown distribution of all these joint distributions. It's like the MCMC and Markov chain Monte Carlo, but it's much faster than that. So it's also very easy to use. Just the two steps. First step, you estimate the model as euro, but this time you could save that model. And then in the second step, and you do the simulation smoothing, and you generate as many samples as you need, and to describe the distribution. And I would use that one example to show that. And here is the well-known airline passengers time series. And it has 12 years monthly data, 144 time points. And to model, you see the trend, you see the seasonal component, and then to model it, you take the log, and then you model it. But now that if we want to know the distribution of the sum of the 1960 forecasting, given that the first 11 years are available, assuming that the last year's data are not available, you want to do some forecasting of 12 monthly data. And you also need to take the exponential of that, your forecast, you sum it, and in all the way, and I think before the simulation smoother, you could get the point estimate of this one. But there is no way to really get the distribution or that you get the confidence interval about your forecast. But now with the simulation smoother, it becomes pretty easy. Step one, you just build your model and save it, just like Euro. And now that it just one more step is use the after model equals option in the same smooth statement. And then in step two, you would set up how many samples you want to use to describe this distribution. This is as shown that in the right side plot. We could use the histogram and based on the 1,000 samples we just get, and to get the distribution of this sum of yearly forecast. And for this case, we know the true value. It's use the red line. And then you could see that this distribution is not the exactly normal distribution, but skewed to this actual value. And we draw the normal distribution, you could compare with it. And of course, you know the distribution, you could get the confidence interval, 95%, 90%, whatever that you like. And you could do anything, in fact, lots of things based on this distribution or that the sampled hidden states. And just another quick example how that you use it is that most of the time that we get the time series, but sometimes we don't want to reveal this true data to the third party. But this is especially in the financial or in the bank, and they would not reveal any true data. Then, what the data you give the third party, and you'd better give the simulated data, but has the same pattern that's in the real data. And how to do that? In fact, this is a very challenging problem. And here is that we use that the cell growth, and this is something is the complex enough. And each small panel is one experiment, and you, for example, 12 hours, and in some plate, you put some cell, you monitor that how it's growth. This is a well-known one, and this is a full experiment, but in fact, behind that, there are 1,000 experiments. But then you need to know what's the growth and what's the pattern for this cell and to grow. And of course, you could use some parameter model to describe this curve, and it's pretty complex. And you even need to know that which path you need to try, and or you need to select. And then, if we go to the this model, the things might get much easier. Is that we just use that let the data tell, and use the non-parametric, or we call it the semi-parametric way, to directly find the pattern. Of course, this, for most of the cases, it should be enough, because later you could describe that the pattern for this cell growth. But here, we just use this example to go one more step, to show you, in fact, you could start to simulate any data and follow the almost same pattern, and based on the true data. And if we could use that the bank data, and you know that it's maybe that more that close to the real world, or insurance data, just that we didn't get the permission to use them. So that's why we use this public data, but to show no matter how complex these things, now it's very easy to simulate the data. And this is the first that new feature we introduced. Now I'm going to talk about some performance improvement. I would talk about two of them, and one is related to the hidden Markov model, HMM. And this is another state space model. And this time the hidden state is discrete and it follows the Markov chain, and then it's often called the hidden Markov model. And I give a picture, and this is from one patent, all that you know that is called SAS Betting Lab. This is the, if you Google it, you could still see that more information. And this one is that what you observe, in fact, is from the video. Some professional that to bet, and then the ball. This is some 2 seconds video, and then we recorded about 500 videos, and then we let the hidden Markov model to find out what's the hidden state behind these things. And now is that for any new video, and by any that anyone to buy it in, and then this could tell that your bet is good or bad, or that which part at which millisecond is good or bad. So this is the patent of the SAS Betting Lab covered. And but for the hidden Markov model, it could go very complex. Then how you find out the true parameter? You go to the optimization problem. And the optimization most of the time is that we use the local optimization. You start with 1 point, and then the gradient, Hessian, and finally you converge to that the minimum, and then that here is the maximum. We want to maximum the log likelihood, and then you are done. You think that you find the true parameter, but in fact for local optimization, you always found one local minimum, but that local minimum have a high chance would not be the global minimum. Here I give one small example in the finite hidden Markov models, 500 observations, and in that case, you only need 12 seconds and to find one local minimum, and the log likelihood is negative 1,000. And but you need much longer, about more than 2,000 seconds to find the global minimum. It should be 10 power to 150 times more possible than the previous one. So to have the high quality solution, or that you have more chance to find the true solution, you'd better use the global optimization. The problem is that it's much slower. So our job is that how to make it faster. The general way in the computer science, right? You parallel it, use as many CPUs as possible. The problem here is just that it's not that easy, because for this problem, it's not the ambitionally parallel problem. You need to use the asynchronous parallel processing, and then thousands or tens of thousands of lines behind that. And but we make it happen. So here is that use the same example, and we only need about 270 seconds to find the exactly same solution, and it should be that 7 times faster than before. This is the first performance improvement, and follow the computer science way to parallel things. And the next one is another way, if that you want to improve the performance, is in algorithm level. Oh, sorry. And for this global optimization and the in-proc HMM, you just need to use this multi-start equals option and to set up everything. And now I go to the next example. And before talking about that, I would first introduce the background about this causal inference or causal AI. And first, that to do the causal estimation, you want to know the effect of the cause, and it's something pretty complex or very difficult. Mainly because lots of times there are so many factors that have effect on both the outcome and the treatment. Then you need to find the way to that eliminate such effect. And also, even there are more complex cases, you need to introduce something called instrument variables. But all these things, we call it correl estimation. We have that tons of procedures to cover different cases, Bayesian way, deep neural net way, and different ways. And then this is here. But how that to model it? In fact, you need the corel graph analysis. This is covered in PROC corel graph. And if give you that the relationship between those variables, that's called corel graph. And then you can know which variable should go into the outcome model, which variable should go into the treatment model. And then you could use the corel estimation method to find out a way and to do that. But who provided the corel graph? Most of the time is coming from the expert. And that's not AI, that's not enough, right? So we are thinking is that if we could use data directly to get this corel graph, and then from the corel graph analysis, then we know that how to do the model. Then based on the model, we use the estimation method. This is the end-to-end, the corel AI. And most of the cases, it's very difficult for the corel discovery. And now that we can use the PROC corel discovery to do that, and here that we give one example. From you observe data and you directly get a corel graph, you do the analysis, you choose that here we choose a deep neural network to help us to find out the corel effect. And but most of the cases, in most of the software, there is no corel discovery. It's this step, how to from the data to find the corel graph. Why that most of the software package would have no such things? That's because this problem, in fact, is very hard, and it's called NP hard. It means that as the number of variables increase, the number of possible graphs, in fact, increase super exponentially. Look at here, only 20 variables, the number of possible graphs already reach the number of atoms in this universe. So it's very difficult to get that. But in fact, 2 years ago, and SAS and provide an algorithm can get that this graph very accurate. Before SAS's algorithm, and the best, I think, the algorithm is to reach 30 or 40% accuracy, but this algorithm can reach 100% accuracy, even that in the 100 variables case. Of course, it needs you to some computation time, and maybe that even 1,000 CPUs, but it's parallel, it's good. Then we challenge ourselves is that could we make it faster? And we did it last year. We invested a totally new algorithm, and it's also that in the patent application, this is some unique things from SAS, is that we make it much faster. Like in the 100 variable case, now the new algorithm is 5,000 times faster. And in the 1,000 variable case, the old algorithm cannot do it. Of course, if you estimate it, it needs about 70 years. And we really didn't do it. But with the new algorithm, it only needs 2 seconds. This is, in theory, we are 1 billion times faster than the old algorithm. So, and in fact, in all these 3 things I talked here, and they all have, in some ways, unique from SAS because we all have the patent application and then implemented. And I really have hope that I have the chance to introduce you more things that in the next year about what's news in that SAS econometrics. And I'm at the booth, forecasting and econometrics booth. And Yeah, and if you have some questions, you can ask me there. Of course, if I don't have time to answer your question here. And also you could email me anytime. Thank you. I'm ready for any question. Thank you.
Thank you, and I will be helping here conduct Q&A, so if there are any questions in the crowd, please don't hesitate to ask. Is there anything from anyone as far as questions? We have about another 5 minutes. All right.
Cool.
Perfect.
Okay. Then, yeah. Thank you very much, everyone. Thank you.
All right, we appreciate your time. Thank you so much. Thank you, Jilong.
Yeah.